So now it's a bit tedious to go through these numbers and see which week is actually or which days and which hours of the days are the most comfortable. That would be crazy to go through this list. Therefore, for this type of analysis, it's better to look at extreme situations. And for that, we have the statistic file or the statistic information, which is we can get with this one. So this actually gives us quite a lot of extra information. Aside, by the way, especially for landscape architects, it gives us also more information about the climatic zone. So for example here, the README text gives me this information. Köppen zone description. This is a cold climate with dry winters and hot summers. Examples are Beijing, China, Seoul, South Korea. So it gives you actually, for example, the Köppen climate zone. And from there you can then select your plants, for example, for that project. But what we are interested in this analysis is the extreme conditions. So for example, the extreme hot week is in August. So in August is the hottest time. The coldest is January, first week of January or second week of January. So just to better understand, the first number is the month, and we have the day and the time of the day. Means because this is a period, it's a time period, it's from 1 o'clock in the morning till 24 o'clock in the night. Then we have a typical hot week, which is this one. This is July. Typical week is October. Hello, October. The cold week, February, and we have the extreme cold week. So that gives us another layer of information, which we're gonna use now. So instead of using our analysis period, we can actually use this as a period. So there is actually the same output. The analysis period, in that case, it's 1 year. It gives you the beginning date and the end date as a list. So in our case, we can just use the extreme hot week as our analysis period, or any of these. And now we cannot really compare this anymore, because this shows the whole year, but this now gives you the output only for that week. So it also shows the week, and so this is the hottest week in the year. And yeah, you can see it's all above 20 and 27. This is in the morning hours, I guess, because it starts in the morning. 1, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, 7, 8, 9, 10 and 11. At 11 it's already quite hot until late in the evening. Here it goes up to 30, 32, 33 and so on. 33, it's really hot already, so that can get quite uncomfortable, and then it cools down in the night. Percentage of cold stress, okay, is of course it's 0 because there's no cold stress during that time. We could look at the percentage of time which is comfortable. 42% is comfortable, which is, I guess, only during the night, the late night hours. Okay, let's kill this. So how can we actually use the data on a project, or how on a specific 3D model? I think that's where we're trying to get to. I mean, this kind of information gives us a lot clue about how the design might need to be. So that can give you quite a lot of answers, and you can use your logic to implement that in your design. But what we want to represent that on a model, and we start with a very simple model, which is just this square. Let's imagine this is a square within your urban context. There's nothing around, it's just a square. So we need two things. We need one component which actually takes any obstacle we design into account, and we need another object which actually represents the output from the perceived temperature onto the model, onto that space. And for that, there are two components in Ladybug, which is, so one is the Ladybug Recolor Mesh. This is This is basically a tool which can recolor the mesh based on the data input and on the mesh on the test surface. Basically works like the others we showed in previous episodes, but it's a more generic version of it where you can input any data as long as the result. But we'll deal with this later, so that goes here. And we need we need something which actually adjusts the temperature based on the model. For that we need this tool, Ladybug Outdoor Solar Temperature Adjuster. So now it's getting really interesting. Location, we need the location. So what this does is basically taking some parts of the weather data and adjust the temperature based on the model. Meaning that wherever there is shade provided at that certain hour, then this is represented in, this will adjust basically the temperature for the certain phases of this test mesh. So, okay, let's just go through and you will understand. We need the location. Basically gives the component the exact angle of the sun. And then we need this component. Either the output of the Gen cumulative sky matrix component for high resolution analysis, or the direct normal radiation output from the Ladybug import E+ weather data component for simple low resolution analysis. So we looked at the Gen cumulative sky matrix in the previous video, so we can look at that maybe later, but let's try the simple low resolution analysis first, as it says here, or the direct normal radiation. So the direct normal radiation you can find here. What I love with these tools is that when you hover over it, it always gives you information what it actually is. What is the direct normal radiation? I also didn't know until I hover over it and just read. So if you don't know what things mean, just check the text. It tells you pretty much everything. I will not explain it now, just have a read yourself. But yeah, this goes into here. Diffuse horizontal radiation, that's just the next one, goes here. We need the base temperature. Again, base dry bulb or mean radiation temperature. I have temperature and this one, which is slightly confusing. Again, I can just read what do we need. So here, a number or list of numbers representing either the outdoor dry pulp air temperature, if the input below is set to true, or the long wave mean radiant temperature MRT of the surrounding surfaces in degrees Celsius, if the input below is set to false. The former is useful for computing outdoor MRT if you only have the air temperature, while the latter is useful for indoor conditions when you can compute starting long wave MRT from the indoor surface temperatures. Yeah, we using the dry pulp temperature for the base temperature, and then we set the base dry pulp or the mean radiation temperature to true because we want to calculate outdoor comfort. And then we set this to true, and then we have, it doesn't say you need this horizontal infrared radiation, but you can provide it if you want. Again, just read what's written here. A number or list of numbers representing the downwelling long wave infrared radiation from the sky. This input can also be the horizontal infrared radiation output of the input EPE component. I guess it's a spelling mistake. The values are necessary to calculate long wave sky temperature when the input above is set to true. So we set this to true, and we need this. Body posture, you can actually calculate what's the effect on the body depending on their posture, if they are standing, sitting, rotation angle, body location. Body location will be important because we don't just test a small area where body is standing. We will test, of course. I mean, that could be also interesting that if this is a moving character, we can like animate a sequence where it goes through different spatial climate conditions. He walks through and then at some point that he is comfortable, then that could be interesting. But what we do is the body location will be a list of locations based on the ground model. So the ground model will be divided, as in previous episodes, will be divided in a grid, and then each of the faces is the body location. So to get a bigger picture of the space. Context shading, that is important. That makes this tool actually run. So not that I tell you something wrong. So all these inputs here are optional. Again, everything which has an underscore at the end is optional, but we need that really for our 3D model. And of course, the more information you have, the better. So if you have information about ground reflectivity and so on, we will just go into this very quickly. But based on these additional inputs, the radiation, diffuser radiation, it also adjusted the mean radiation temperature, and we can add this here and it will slightly update the perceived temperature. So if we would look into that, if we just make another copy of this, which we can, and then disconnect this here and create a copy of this panel, you see that the numbers have slightly changed. So again, the more information you have, the better. Now what we want to do is to add, what we're gonna do here to make things simpler, let's just add another block here which is called data, and I'll feed this in here and put this, exchange this here because it's gonna be easier to change. We will connect more strings here for other components, and then it's easy to swap out the different weeks with the different conditions. Okay, back to here. We need the context shading. So BWrap, that can be also a mesh, by the way, but let's, because we have here, this is our context, let's say, context shading, and it again calculates. And then for the body location, so we want to have this test surface to define our locations. For that we use a component called generate mesh. It's also a ladybug component. This is my generate mesh component. This will need the test geometry, which is this one. It creates a mesh out of my test surface. I use BWrap. You can also use just a surface or rectangle, depending on what you have. I hide it here, add it to my test geometry. Grid size, again, that's what we did in the previous episodes as well. Maximum 10 meter, minimum I would say 0.5. Less digits because otherwise it becomes tedious. Okay, 0.5, maybe even smaller because our test site is very small. But we always start with a large grid size. That might be too large actually. But let's say 5. This is my grid size, distance from base surface. We also discussed it before. Also don't want to see this. I'll explain something about that in a minute. And then move test mesh, set to false if you want test mesh not to move. Yeah, I don't want this to move. So we can use the same true as here. And yeah, that's our test mesh. And now we can put our test points into here. But basically, this is the body location. Test points is body location. We don't need to see this. Okay, looks good so far. Of course, no, we cannot see anything yet. But let's make a quick excursion into customizing previews of things, because I don't want to. So if this is selected, it's green. If it's not selected, it's red. I don't want to see that. So what we can do is actually create a material. Nah, it's not what I want. let's go here. Sometimes easier to find things in here. Display, yes, that's what I want. Preview, custom preview, that's what I want. So I can put this here, and you see it turns into that crazy color here. Can turn this off, and then I can add a material, create material, and can set the transparency to something like 0.9, and that immediately gives me this kind of outlined but transparent thing. So that's good because I can still see where this thing is, but it doesn't influence, or it doesn't greatly influence my... You could also just add a slider here, it's also possible, and with that slider just change the transparency. What else do we have? Shininess. Yeah, of course you can play around with these things here. It can add a kind of a shine to it. I don't need that. Or maybe, yeah, let's keep it. Maybe it's cool. Diffuse color. Color swatch. That's what I want. That makes it easier. I can set this to white, for example, or black. White feels better. And then transparency higher. Let's organize it in this way. So we have our test surface and we have our context on one area. This is our data area, this is our adjustment section. This is where we calculate the climate index. Sorry, the outdoor comfort calculation. And this is where we recolor the mesh. I hope you could follow so far. We can quickly repeat. So we built a typical setup for retrieving our data. We were talking about Korea, when is the best time to go to Korea. We added the climate data for Seoul, and we opened it with these two importers, which is the weather data, and then we have some statistics, and we looked at the different weeks and if they are hot or not hot and so on. And then we were feeding this into the outdoor comfort calculator, which calculated the perceived temperature for every hour of the day. But now, because we actually added a model to it, we added a model with a context which is adjusting the shading, adjusting the temperature, with the solar adjust temperature component, which takes a bunch of other things into account. And because of that, we created a mesh with a grid of 5 meter size, and that basically creates an output here where you can see that it not just gives me the temperature per hour, but also for each of the grid cells. So this would be grid size 1, 2, 3, 4, and so on. So it seems like there's only 4. And we're using the extreme hot week as a data period. Now, if we want to recolor our mesh, we need to provide the mesh. So we need the analysis report. We need the input mesh, which is here, and we need the output data. Oh, it's red. Why is it red? Because currently there's way more data than the mesh. There should be only 4 data. There should be only 4 values, right? So, but we have 700 values. So what we need to do is we need to create an average, but that doesn't work because there's text and numbers. So what do we need to do? We need to first separate the numbers from the text, which is with this component. Input list and numbers and strings. So from numbers we have basically 4 data blocks with 168 values. If we put this in here, we're gonna create 4 values. Okay, it looks better. Now we need we also need to flatten this, because let's kill this. So if we don't flatten this, it actually gives us 4 separate branches of data, which this component cannot read. We need to flatten it. Now we could, of course, then we can change the grid size to, let's say 0.1. No! No! You shouldn't have done that. Okay. Well, so what I did was completely wrong. Sorry for that. Actually, so I had to restart everything because the program just was frozen for a while. Actually, no, it was not frozen, but it took way too long to calculate. So I stopped the whole process and then restarted. 2 things what I put wrong was, first of all, I said true here, but it should be false. So that's one issue. The second was that the problem is, at the moment, is that this component calculates the entire year. So it calculates the entire year and then it passes the information on to this component, and then it selects the period. But the problem is that this is the work intensive component. So we actually so we could run, of course, the whole year, but it takes really long if we lower the resolution. So what can we do to improve? There's another issue with the whole thing, is that at the moment it takes an average. So the output is actually an average of the average for the whole week, and this is not ideal because we want to know the most extreme situation. So we want to check much more detailed on the specific time of the day. In this case, an average output is not ideal really to design, for example, a program. If you have a big park and you want to think about the different program in the park, then it would be a good idea to know during which time of the day you have the best conditions in the different areas of that park, and how can you then even improve that. If you only give an average, then you won't know much about it. Okay, so what can we do to first improve the speed of this whole calculation, and second, how can we cycle more in detail through the data? So here what we want is we want to actually define the analysis period in this stage here. That will make this much more faster. But because this component doesn't take the analysis period twice, it doesn't like that. We already tried that. We need to find a workaround. So what we do is so first of all we turn it off, just not to run into issues again. What's fine is we can put this here. That's okay. But because so what we get as an output from here is already based on the analysis period. But then we design the analysis period again. That was the reason why that made some issues. So what we need to do is to select from these data, so the data I'm inputting here directly, which is the dry pulp temperature and the wind speed and the relative humidity. We can individually select the analysis period from these data streams, and then put it back into here. There's a component for that, and it's called, the component we need is the average ladybug average data. So this would give us the option to actually choose the average data, but it also gives us the option to choose the hourly data. It's a bit of a misleading name, I feel. So these are 3 different streams. So let's create 3 different, 3 of these components, and then we get the dry pulp temperature, the wind speed, and the what is it? Humidity. So, and we're gonna disconnect this here. Dry pulp, wind speed, relative humidity. Okay. Hope it's better now. It seems like the microphone was a bit off. So basically we disconnected this data streams, and then we inputted it here, so where we can actually choose the analysis period. So that gives, so now we can use this thing here. We just go into here, here, and here, and we also disconnect this here. Basically what we do, we limit the amount of data before we do further calculations, which will make the calculation much faster. Let's examine the output. So what do we get here? And at the moment nothing, because we need to first turn it on. So let's turn it on. So now the calculation was much faster, and we should get 174 values, which includes also this beginning, the text. And here we can select the hourly data. That should actually give us the same amount of values. Yeah, so here we get from the data we get 175 values, but here we get 2800 values, because we get for each phase of that mesh we get 175. So in order to get the same result that we got before, we need to average the output, and we're gonna do it like this. We gonna add a component which first divides strings from numbers. So we have strings, which is basically the text in front, this stuff, and then, or even lists. This will all be kicked out, and then we get only the numbers. And the same we do with these components. So basically from here we can then decide either the hourly data or the average data. So just to get to the result we had before, we're gonna average this. This is the same component as this one we already used. And we can turn this on as well. Yeah, at the moment it doesn't work because it is missing. So we average this. We don't need to flatten it this time because it's already flattened. There's only one stream, only one data path. And this is the dry pulp temperature. It goes here. Here, wind speed. Yeah. Okay. So now that ran much faster. I will save that, and now we can actually decrease our grid size. It should be much faster. Yeah. So that was much faster. That was much faster than before. Yeah, so that was much faster. So just to recap a bit, so we don't lose track, I had to actually change a bit here, so because it didn't give me some errors. But so what we did, we instead of like going directly from the weather data into the outdoor comfort calculator, we separated the different streams of dry pulp temperature, wind speeds, and humidity. Reduced the data by selecting the analysis period for each of these, and with the data stream we can select very comfortably, very quickly different week. Then we get, in order to get the same result as previously, we average the data, so we get an average number for the temperature, for the wind speed, and for the humidity for the whole week, for the period we chose. And in the adjuster, in the solar adjustment temperature module, where we calculate the mean radiation temperature based on the model or the shading device, just to better understand, adding more here. Add both of these to our context. The context, let's rename that. Context gets fed into here, the context shading, and that will adjust or recalculate the mean radiation temperature based on the location, the normal radiation, diffuse horizontal radiation, base temperature, and horizontal infrared radiation. And it gives us, based on the body location, which is basically all of these points, because we want to test the entire surface. Okay, wait, let's have a look here. So instead of like testing only one location, we're testing all of these. For every phase of that mesh, you get 175 values, which is always the header, the titles, and what it is, the period, and then for each hour of the day you get a value, and this basically for each of these phases. Maybe we can show it in a tree parameter viewer. Basically each of these phases is represented with one spot, and you can see there are 169 from 0 to 168. We in this component we're gonna divide the numbers from the strings, so we can calculate an average and feed the average in here. So there's an average for each, an average number for each of these phases, and that's get combined with the average dry pulp temperature, wind speed, and relative humidity, which is always just one number. Output is 169, because this is basically 169 values, which is basically for each is one value for each of these phases. Again, we can actually, we don't need this here, we can remove this, but we need to make sure that this is flattened, that the information is flattened, so it's one list of values. And yeah, that's here we're gonna get the output. So you can see here all the values for each hour, and the same, and here the average temperature. But that's not yet really ideal, because what we want is we want to scroll through each hour of the day to really see what's happening during lunch, in the afternoon, and so on.